My name is Nino Michniuk, as already announced. I'm a student at Kaiserslautern at the University of Applied Sciences in Germany. And Altern, our university, collaborate in a lot of projects. One of it is the feedback-controlled multibody simulation of an exoskeleton describing a human walk movement. This is done by performing co-simulation between the software packages Actuate and MotionView, MotionSolve. And all the joints are actuated by controllers in this animation you can see here. These are the final results. And today I'm going to show you how I built this entire model and how I set it up by going through the following contents. And first, some task specifications to give you a quick overview of what I had to do. And then I divided the presentation in two main parts, the multibody simulation in MotionView, MotionSolve, and then the controller design with Actuate. And I will quickly give you an overview of the recent activities at our university. To the task specifications, the purpose of this project, Altair contacted us because they wanted to create some kind of a library with advanced examples of multibody models to show potential customers the usabilities and strength of MotionView, MotionSolve. Therefore, these examples must meet a few demands. You can see them at the right, like good-looking geometry, visible advantages, and something like that. And one of these examples was the exoskeleton describing human walk movement, which I built. And some facts to the modeling. This is an exception of the model description. Obviously, I had to use MotionView to represent the exoskeleton. And I had to use flexible bodies that allow stress contours and deformation. And I had to include a human dummy. And in the beginning, I had to drive the exoskeleton with motions and validate its behavior in MotionView, MotionSolve. And there's one sentence of this model description which you can see at the bottom in blue. Starting from the rest, the exoskeleton sits and stands up, walks 10 steps and turns around and returns to its initial position. Because this sentence helped in the beginning to build some kind of a task cycle of the tasks which I had to model, like standing up, walking, turning around and sitting down. This was some kind of an orientation in the beginning. But to perform these tasks, the first thing I had to do was to build something which can perform these tasks. So we received this CID data of this human dummy, which you can see a sketch of it at the right. And what I had to do is to decide where to put which joint. And I've used this parameterized human, which you can see at the left, by Winter, which is based on an entire height age. And knowing the height of my human dummy, it was then easy to place the leg joints at certain positions. These are all revolute joints. You can see the coordinate system at the right. The degree of freedom of these revolute joints is about the z-axis. And each leg consists of 3 joints, one for the hip, one for the knee, and one for the ankle. And all the remaining bodies of this human dummy are all fixed to each other. Now I had to link the upper body somehow to its environment, and I've used the orientation joint, which leaves the degrees of freedom, the translational degrees of freedom, so it could move forward, backward, sideward, up and downward, but it constrained all the rotation. So this would be later important, so it can't fall over during walking or something like that. And though I didn't want it to fall upwards, I've added a floor and basically used context between the feet and the floor so it doesn't fall in the direction of gravitational acceleration. So when I now put all the rotational angular velocities in the joints to 0, the dummy was able to stand. But standing wasn't a task which I had to achieve, so I've used motion capture data. This was the basic idea to get some motions into it. And I've added the hyperlink here, an open source database which has a huge amount of motion capture examples. One of it can be seen at the left, this dancing guy. So it was easy for me to get these basic tasks like walking or standing up and something like that. This is what I downloaded there. You can see then these are the angle displacements which I downloaded, consisting of in each leg standing up, walking 5 steps, with 2 legs it's equal to 10 steps, then turning around, again walking, turning around, and sitting down, which is basically just a reverse standing up of the angle displacements. But the human dummy didn't turn as required by just making some leg movements. So what I had to do is adding an external motion about its y-axis. So it turns to precisely minus 180 degrees when it does its turn, and then in the end to its initial angle. So by that point, I had a human dummy performing all the desired tasks, but I didn't have any exoskeleton in it. There were some issues in the beginning, and I received an updated CAD model of it by that time. And the idea was now to fit the human dummy into the exoskeleton, let it perform its entire movement again, and use hypergraph to read the angle displacements of the exoskeleton joints to use them later to actuate the exoskeleton instead of the human dummy joints. This worked pretty fine. You can see them here. Look pretty similar to the first one I've shown you, but you gotta trust me on this, they aren't. And what I additionally did here is I've shortened the resting phases in between the single tasks to make the entire simulation a little bit faster. This worked pretty well. This was the first successful simulation of my exoskeleton performing the tasks like standing up, walking 10 steps, turning around, and returning to the initial position. So what I wanted to do then was adding the flexible bodies, and that caused a lot of troubles and errors, and the runtime went to infinity. So I had to do some step backward to refine the model to make it more robust. And the first thing what I had to do was to adjust the contact method, because I've used the Poisson method at that time. And one of the Altair's engineers told me it's more convenient to use the impact model for the continuous contacts which I had, because at least one of the feet was always in contact with the ground. And the second thing which caused the errors were the discontinuities which I had in my motions, because I worked with sensor events to that time. For example, in the beginning, my dummy was able to lean forward to get its center of mass near to its feet to stand up properly. And when it reaches a vertical upper position, the sensor event detected it and set a constraint. This worked in the first model pretty fine, but didn't work when I used the flexible bodies. So what I did is I just exported the angle displacements again, adjusted them a little by hand to have a continuous motion, which I then could use to add flexible bodies to the model. And they allow deformation, and I could display the stress contours, which can be seen in this figure and in the next animation. I've added this because at that time this was my bachelor thesis, so I had some kind progress of this entire work here. And quickly mentioned, my job was not to evaluate these stress levels, I just made it able to display them. So I can't say anything about that. Please don't ask me about the stress levels in the exoskeleton. And then, let him quickly finish, continued my work as a master's student in the so-called research and development module. And the goal here was to deactivate the motions I had and to replace them with certain controllers in Activate, and to perform co-simulation between the two software packages. And the idea I had was, because I already got these entire angle displacements for the movement, to build some kind of a feedback position control which delivers certain torque to perform the movements in form of a cascade control. So the idea can be seen here. I've decided to use all the information I could get, like angle displacement, the angular velocity, to then get the torque as an input to my multibody system. This would be the controller for one joint, but to build this controller I had to do some preparations. This can be seen here. I had to do some replanning of the task. I will get to that in a minute. I had to then to redefine the set points for the controllers. Could then do the actual controller designing, like parameter setting of the PID controllers, to then perform the co-simulation. To the task planning, this was the old task cycle, which I've already shown you. And I had the problem that the entire movement was like two-dimensional, and he was always walking on a straight line, as you've already seen it. And the entire turning around part looked really strange to me, because stepping like up and downward on this point. So I decided to change that a little to standing up, walking diagonally across the floor, and sitting down at the other corner of the room. So the leg movements I had to plan was simply standing up, walking, and sitting down. And the diagonally part again comes by an external rotation about the y-axis of the entire system. Additionally, to avoid these discontinuities I have already had and didn't want them to have again, I wrote a little script. This is a code example where the user just had to input the location and the value of the extrema and an increment. And what the script does is to generate a third-degree polynomial in between. So I had this continuous motion guaranteed. And by that, I then added my new set points. Again, the leg angle displacements at the left, and consisting of standing up, 5 steps in each leg, sitting down. And the rotation about the y-axis, which is a quick turn to -1 after standing up, stays at -1, so it walks diagonally, returns to 0, so it could sit down looking forward again. So I could then go to the controller design, and I have to mention that I wasn't really experienced in control design at that point, so I've tried some ordinary strategies which I've learned in control theory to try to tune my PID controllers. This didn't work at all. But what I did know was that MATLAB Simulink comes with a great PID tuner. And I couldn't just simply use import the multibody system into Simulink. So what I did is I used a unit step as an input, recorded the step response, which you can see in blue at the right figure, and I've approximated it by an PT1 element. I could then rebuild this approximated system in Simulink to use its PID tuner. This worked really quickly and get some really great results for the parameters. And I did this for the inner 2 loops, and for the outer loop, I just increased the proportional gain until a certain behavior occurs, which you also can see at this figure. Unfortunately, this controller tends to oscillate during the single leg contact while walking. So I decided to add another simplified, modified position control where I left out the inner torque loop. And this worked pretty fine without any oscillation. These are the controllers I've used in the beginning animation, which you've already seen. Additionally, what I did is, because I had some time left, I was thinking about building some kind of as simple as possible balance controlling. What I had in mind was just simply measure the distance between the feet and the hip and adjust the angle of the upper body according to that distance. And this worked surprisingly well for slow movements like standing up and sitting down, but unfortunately it didn't work for walking. So the model is similar constraint to the beginning, what I've already mentioned with this orientation joint, but I've used the balance controller to somehow create a more realistic movement because it leans forward, backward during walking, and it looked much better than in the beginning. The co-simulation part, I've just added this slide to make the presentation complete because this worked everything pretty fine, not much to say about that. I've got this MotionSolve plant in the middle where the multibody model is in. It is in this block, and all these little squares are my controllers with the in and outputs, and not much to say about this. The results, I've already mentioned that. Unfortunately, the Position control tends to oscillate during the single leg contract. This is the result of the right knee. I've zoomed it in at the right to make it more obvious. This is probably because I've used the derivative gains in the PID controllers. I didn't know that at that time to avoid these, but this would be a great entry if any student of our university should continue this work. This would be a great entry for that, to avoid these derivatives gains. Some recent activities in our university, the exoskeleton I've just presented to you. Parallelly to my work, another student worked on this prosthetic leg, which was some kind of co-simulation between Simulink and MotionView, MotionSolve. During his documentation, he noticed a big mistake he made. So we're currently looking for another student to continue his work because it didn't work because of this mistake, and he was searching for weeks for it, and he just noticed it during the documentation. Another thing is the so-called acrobot. It's a double pendulum with its actuator in, I call it, elbow joint, and the goal is to swing up and balance it in an upper position. And a student just implemented the co-simulation between actuate and MotionView, MotionSolve, but he just did the balance controlling part. And this would be an interesting model for another student because we got a physical model built at our university. We could then compare the results of the simulation and the real model. What I'm doing currently is this. There's a simulation of a bipedal robot I've done with MATLAB Simulink because I wanted to be more independent in the software and I needed some guidance in control theory, and there's MATLAB really great with it. And this model has all 6 degrees of freedom to its environment and balances just because of the control theory behind it. As a student, I have to show you the literature I've used. And if there are any questions, I'd be happy to answer them.